This webcast continues and finishes part 1 of the Projectile Motion Lab. Let's see here. So I just want to talk about the last couple of questions in part 1. So we found a physics equation for the graph of the projectile's range versus the initial velocity. And so what this is telling us is that for every additional meter per second of velocity, the range increases by 1.4 meters. Okay, so as the I'm trying to find the graph here. As the initial velocity increases, the range also increases. And for every additional meter per second, the range increases by 1.43 meters. Okay, so the next question is there a physical significance to the slope of this range versus initial velocity graph? And I want to just point out that, let's see here, that the here we go, that our slope, which was 1.428, is very similar to the flight time that we found. And remember, the flight time didn't seem to change. Like, as we increased the velocity every time that we launched the pumpkin, it took 1.43 seconds to fall to the ground, no matter how fast it came out of the cannon. Okay, so let's say that. So here in part H, we'll say the value of the slope of the range versus initial velocity graph was very similar to the flight time of the pumpkin. So let's see here. The slope had a value of 1.428, and it was meters over meter per second. And the flight time had a value of 1.43 seconds. Okay, so the values are pretty similar. 1.429, that rounds to 1.43, and then we had time of 1.43. Let's look at the units of that slope. So I'm going to say also the units of the slope simplify to be seconds, which is the same as the unit of flight time. The slope units are simplified below. And let's show how that happens. So we had units of meters per meter per second. And let's see. And when you divide by a fraction, you can bring that out and multiply by the reciprocal, right? Well, the reciprocal of meters per second is seconds per meter, right? I'm just flipping it upside down. When I look at it this way, meters can cancel because I have a meter above the fraction bar and a meter below. And so that equals seconds. So, therefore, let's see, let me make this blue. We conclude that the slope of the range versus initial velocity graph has a physical meaning, which is the flight time. A general model of this situation can be found by replacing the numerical slope, right, the 1.429 1.429. We're going to replace that number with its meaning. Okay, so let's do that. So in our physics equation, we said that the range equaled the slope times the initial velocity. Well, our slope is now the flight time, which is like the elapsed time, times the initial velocity. Okay. And I'm sorry, I think I said this wrong in the previous webcast, but we have seen this before. In Unit 2, we said that the displacement equals the velocity times time. Well, look, these are the same equations, the same relationship. And so anyway, so that is the answer to the question. The slope has a meaning, which is the elapsed time, the flight time, delta t. Okay, then in step 8, it asks us to make a graph of the flight time of the projectile versus the initial velocity. So I'm going to go back to my original data. Now notice that initial velocity is in the column on the left and the flight time is in column C, so they are separated by column B. Now you could copy these over so they're next to each other, but one way to do this, I'm going to highlight all of the cells for the numbers that are initial velocities, and then I'm going to hold down the control key. I am pressing the control key and holding it down, and now I'm going to select the flight times. So do you see now I have selected these two columns, and so now I can just go insert a scatter graph. And look at this. I'm going to move it over here to the right, so it's not on top of the previous one, and just make a nice label here. So this is a graph of the flight time of the projectile versus the initial velocity. So I have initial velocity, meters per second as my independent variable, and I have flight time in seconds as my dependent variable. So what do you think about the shape of this? It's like a horizontal line, right? I mean, it is linear, but what's really important is that it's a horizontal line. It's a line where the slope is always 0. When you see something like this, it basically is telling us that the initial velocity does not have any impact on flight time. Flight time does not depend on the initial velocity, right? No matter how big we made initial velocity, the flight time did not change. And so that would be what we want to say here. So we would insert that graph, and then when it says what kind of relationship exists, I would say something like the flight time does not depend on the initial velocity. The graph of flight time versus velocity is a horizontal line, which means that as velocity increases, there is no change in the flight time. Okay. So this concludes the first part of our lab.